So in another video, we looked at Hess's law with respect to enthalpy, delta H, and we'll refer you back to that for some of the details in terms of setting up equations. Here we want to apply Hess's law to look at the Gibbs free energy of formation. And again, we're going to look at the formation of gypsum when we react anhydrite with water together to get the mineral gypsum. So the Gibbs free energy of formation can again be determined using a variation of Hess's law. Hess's law says that if we are looking at the formation of elements for anhydrite, water, and gypsum, then we can combine those values of delta GF and then get the Gibbs free energy of reaction for this thing here. So what is that going to look like? Well, the shorthand for that, taking a shortcut given what we've looked at earlier in terms of enthalpy, we'll simply write that the Gibbs free energy of this reaction is equal to the Gibbs free energy of formation for gypsum, so those are our products, minus the Gibbs free energy of formation from the elements of anhydrite, minus the Gibbs free energy of formation from the elements of water. And we've got all those in these tables here. So for this value here, this is gypsum, the delta G for formation of Gibbs free energy of the elements is shown here. That's in joules, so we'll convert it to kilojoules. So that is minus 1797.2. And then we'll subtract from that the value over here of 1321. So minus 1321 point, well, we'll just call it 7 for now. And then minus, and then we've got another negative value for water, which is down here. So that is minus 237.1. And so if we sum all those together, then the total that we get is 1.3, or minus 1.3 kilojoules per mole. So now we have here the total Gibbs free energy of the reaction, not formation from the elements. We already had that. If we wanted to know Gibbs free energy of formation from the elements for gypsum, well, we don't have to do any calculations. It's given to us right there. But this is not the formation of Gibbs free energy from the elements. It's the forming gypsum, this stuff here, from compounds that already exist. And this reaction, these data are not given in these tables, but we can extract it by using this variation of Hess's law. Hess's law can be applied not just to delta H to get an enthalpy of reaction. It's supposed to be a delta. We can use it to get a Gibbs free energy of reaction or a delta S of reaction. Anything that is a so-called state function. And when we talk about something that is a state function, it means that it is independent of the path. We don't care how it is, what kind of molecular rearrangements happen to take anhydrite and react it with 2 units of water to get gypsum, which is CaSO4 times 2H2O. Remember that times, it's not really a time sign. The dot 2H2O means we have 2 molecules of water that are being attached to the calcium sulfate units to make this whole thing that we refer to as gypsum. So when we get the free energy of this reaction, it doesn't matter how these things break apart or combine to get from here over to here. So that makes it a state function. The enthalpy of the reaction doesn't matter on the path. The Gibbs free energy does not depend on the path. The difference in entropy does not depend on the path. So since it's all independent of the path, we can apply Hess's law and make these kinds of calculations. Now the final part is, let's take a look at this value that we got. It is 1.3 kilojoules per mole, or let's just make it in joules, 1,300 joules per mole. That's not very much. Well, at least compared to boiling a cup of coffee. For a fun little calculation, figure out how much energy it would take to take a cup of water. A cup of water is about 128 grams. And you can multiply that, that would be the mass, times a heat capacity of 4.184 joules per gram dot mole, and then heat it from, let's say, 25 degrees centigrade to 100 degrees centigrade, so close to room temperature up to boiling. So if you wanted to boil a cup of water, that's going to come out to about 40 kilojoules per mole, and the difference in energy here is just 1.3 kilojoules. So much more massive than this puny value here. So what does this mean? Well, for this to be negative, it means that the Gibbs free energy of gypsum is lower than the Gibbs free energy of the sum of calcite and water. So not calcite, anhydrite. So if we look at anhydrite plus our 2 units of water to give us gypsum. So if we look at the Gibbs free energy, and we have gypsum over here, and then anhydrite plus water over here, the Gibbs free energy of gypsum is going to be less than the Gibbs free energy of anhydrite plus water. So what is that difference? Well, that difference is energy is about 1,300 joules. What it means is that if we have a system that's sitting over here, it should spontaneously make its way over that activation energy barrier, however small or large it might be, and then end up in this lower state. But if the Gibbs free energy difference is very small, if the Gibbs free energy is very close to one another, so let's say, we draw it so these are almost the same in terms of the levels of their energy wells, then it might be easy to go back and forth. Maybe adding a little bit of salt to the water or changing the temperature a little bit might raise the Gibbs free energy of gypsum relative to anhydrite plus water. And we might be able to sometimes go one way and then sometimes go the other. And if that were the case, that might explain why we might find either gypsum or anhydrite in various sedimentary deposits. And when we come back, maybe we can look at the equilibrium constant and how it varies with temperature to see what happens if we increase the temperature. What will it do to the relative Gibbs free energies of these things? Will it always be negative if we write it this way? Instead of a difference of 1,300 joules here, could we reverse and have a case where the anhydrite is stable with water relative to gypsum? Well, who knows? Maybe we could do some calculations a little bit later and try to demonstrate, take a look at the issue.